Good afternoon, everybody, and welcome to this IMechE online event. I hope you can hear me okay and you can see me okay. My name is Professor George Agidis from Lancaster University, and I am the Professor of Energy Engineering at Lancaster, and the event it's on application of artificial intelligence in leakage management in water distribution networks. This event is organized by the IMechE and the Fluid Machinery Group of the Power Industries Division that I'm on the board of. And the presenter today is my PhD student, a final year PhD candidate at Lancaster University, Ahmed Negm, that he has graduated with an immense mechatronics degree from Lancaster University. He has a Dean's Award Best First Year PhD Candidate nominee and shortlisted for Best Concept in Development in Eco-Innovation Northwest Awards. And his research revolves around exploring the best machine learning models for applications in the water industry. And deep reinforcement learning materializes all of the industry's hopes towards real-time experience-driven and reliable control, and therefore become the focus of these studies. So without any further delay, I will pass it over to Ahmed to start with his presentation. Thank you.
Thank you, George. I'm gonna share my presentation with you guys. I hope you guys enjoy it. I'm happy to see that there's so many people attending this event. So as George said, our application is going to be on the application of AI leakage management in water distribution networks. So here we go. Now, the application of AI for leakage management in water distribution network is a very wide task. So before we start, I'm gonna introduce our agenda for today. So we have a 5-step agenda. We start off with introductions, explaining the presenter, myself, our team in Lancaster University, and our industrial supervisor at Design Network Solutions. I will then also introduce the AI field as a whole and a further dive into the AI in water distribution networks and water management in general. After that, I'll explain the niche of today's event, which is deep reinforcement learning, and any applications of deep learning in the water industry in general, so that we can have a good idea of how deep learning has influenced the water management practices in the engineering industry altogether. Hopefully, this will give the attendees an idea of how we could use deep learning and artificial intelligence to classify certain issues such as leakage detection, or even solve and aid in decision making of other issues such as pressure control. So myself, so as George said, I'm a final year PhD in Lancaster University. Just recently submitted my thesis as well, so hopefully that will be done soon. I have a couple of publications that relate to leakage management. So one of them is a review of leakage detection that was published last year in 2023, and the other is water pressure optimization using Q-learning, which is a section of reinforcement learning that is widely used. So it's one of the basic building blocks of deep reinforcement learning. Now, recently, this month, I've published another paper that's very relevant to today's presentation called the deep reinforcement learning challenges and opportunities in urban water systems. So I recommend, if you find this presentation interesting, to go and check that one out. It has a full classification tree of all the deep reinforcement learning algorithms known, and on top of that has a full review of deep reinforcement learning in urban water management. So this includes stormwater systems, waste water systems, water distribution networks, and raw water systems. So we'll review more of that as we go. So our work is funded by CGE through the help of Design Network Solutions. So CGE is the Center for Global Innovation. So Design Network Solution are the people who approached us with the idea for this project and helped us acquire the data needed to carry on with this research. Also gives us a more engineering perspective to how to apply these deep learning. And this is very crucial to applying any sort of artificial intelligence into an engineering practice. You need to be able to think of both sides, and this is why holding this event is essential, so that you can have an idea of what it looks like on the artificial intelligence side and what it will look like on the engineering perspective. And Lancaster University. So our team at Lancaster University consists of myself, my supervisor, Professor George, who introduced me and is an IMechE fellow, and we have Dr. Jiandong Ma, who is also my second supervisor. So through the help with Lancaster University, you get access to all the researching needs, all the researching material needed from the library, publication hub, and also having a bigger research community that can aid with anything that has to do with the research. In addition, we also made use of the high-end computing that is available in Lancaster University campus, which then accelerated the use of deep learning models and deep reinforcement learning models. Now, leakage management in general can be classified into three main sections. So since we're talking about leakage management today, it's essential to know these sections. We have leakage assessment, detection, and prevention. Assessment is to know how much or quantify the amount of leaks that are in the system. This includes real loss and real avoidable loss, real unavoidable losses, and apparent losses. Some losses are not actual leakage, but when you're having a look at the minimum night flow, or you're doing a top-down balance sheet, you realize that there's some water that's basically unaccounted for, but it's not actual water. Maybe it's unbilled consumption, or even people tapping into the water, like stealing water from the water utility. Now, leakage assessment can be brought down to three main sections. You have your top-down, which is basically using a balance sheet to identify where the water has gone. This is the simplest and the first method used, was coined by Alan Lambert in the International Water Association, and has been used ever since with water utilities worldwide. Some of the definitions and how the balance sheet goes is usually customizable and dependent on the water utility that you're dealing with. The bottom-up balance is, instead of looking at the holistic, instead of looking at the outer appearance, you want to, this is where you look at each section specifically. So you have the minimum night flow, which is the flow of water around 3 a.m. to 5 a.m. This time of the day shouldn't have much flow, since most people are asleep. So any flow during that time can be considered a good representation of leakage. If you have high flow during minimum night flow hours, that means that there is a chance that there is some leak in the system. There's more ways to quantify that. There is a net night flow, there is actual night flow. So there's better ways inside the concept of minimum night flow to quantify leakage. There's also burst and background estimates, which is called BABE. This is a method used to estimate the amount of water that's lost through bursts. And you also have water and wastewater balance. So this is when we collect wastewater, we account for any water that's been used outside and measure the water distributed compared to the wastewater received. There shouldn't be too much of a discrepancy between them. The discrepancies should be limited to things like watering the garden. But other than that, most of the water distributed should be coming back. So any big discrepancies between that also assesses leakage. And you also have your performance indicators such as ILI and more IWA mandated performance indicators. There's there's more to leakage assessment than that, including software methods to identify leaks, and you could read up more about that if you want to. Now, leakage detection is one of the hottest topics in leakage management. Um, Going into that is a very deep dive and will require you to have a look at the review papers, but there's three main points to leakage detection, three main actions to do, which is to identify the leak, so identify the presence of a leak in your network. And then from that, so now that you detected, identify the presence of the leak, leakage detection also involves localizing the leakage. So you want to find out where your background leakage or your burst leakage is. Background leakage is by definition is a leakage that you can't really detect, so that doesn't actually fall into leakage detection. Yet you know is in the network, so you have to mitigate for it somehow. And then pinpoint is to know exactly where it is, so you can send out employees to fix or mend the leak, or even replace the pipe. So this is leakage detection. There are many methods involved, like hardware methods, software methods. Hardware methods include in-pipe inspection, robots, even external methods such as using thermography, using ground-penetrating radars, and even the most commonly used method for leakage detection is actually acoustic measures. So using either um, a listening stick or other methods that fall into the acoustic area can actually help with leakage detection. Now, when it comes to leakage prevention, this area is less researched. However, there is still a lot to read about that. There is two main sections to leakage prevention, which is pressure control. So we should all know that leakage is directly proportional to pressure. And the more that you can control pressure through either valves or pumps, the more that you can control leakage in your system. Now, this proves as a method to solve both burst leakages, so deal with burst leakages at the time, or even background leakages that you might not be able to detect, which is the only method really to solve background leakage. So, is to behave with a mindset that there is background leakages there, and we want to control pressure in this area. And finally, asset management. So when it comes to asset management, this is a topic that is very popular nowadays, where you want to produce a prediction model to find out whether the assets that you have, including pipes, pumps, valves, are going to live for the next couple of years. Are they going to cost more to fix than to replace? Whether you should fix or replace them is the main concern of asset management. However, there should another concern should be to how to fix them and include more research into mending your assets rather than replacing them, which isn't really a hot topic right now, but it is something that some water utilities are looking at. Now, asset management is a prediction or assessment tool, and assessing the conditions of your assets can be used through deep learning, for example. So you can classify whether this is a time to replace or whether this is a time to fix a pipe, for example. Now, this table is an excerpt from the role of deep learning in urban water management, a critical review. This includes a huge section about deep learning in water distribution network, which is currently the trend with artificial intelligence. So on the left-hand side, we have water supply, so water distribution networks, and we have also urban wastewater systems. We want to focus today on the water supply. You have forecasting demands using long short-term memory and CNN, so convolutional neural networks. So you can use historical demand to predict future demand. This makes it easier to deploy optimization algorithms or to even account for future demand that if you don't make provisions for might increase failure rates in your network. You also have leakage detection and localization using CNNs. There are a lot of other methods of artificial neural networks or deep neural networks to solve the leakage detection problem. But this is one of them, using CNN's convolutional neural networks to classify whether there's a leak through signals in through pressure readings or flow readings in the network. So that one is very straightforward. If you use a classification algorithm, you'll be able to pick up trends between signals, pick up trends of pressure flows, and classify whether this is a trend, this is a signal that shows a leak in the network or it isn't. A lot of research has been gone into that and has shown positive impact in reducing the effect of leakage. If there is a leakage, we need to know it as soon as possible and fix it as soon as possible. We also have deep reinforcement learning highlighted in yellow. So this is this is what we're going to be focusing on, is using deep reinforcement learning to actually control our network. So rather than just identifying and then doing something else to it, you can actually use deep reinforcement learning to control your day-to-day operations. You can control your pressure valves in a more acceptable way. The current practice is to forecast demand and build and use evolutionary algorithms such as differential evolution or genetic algorithms to suggest the best way forward. Now, in terms of optimization power, that is great. However, the forecasting is always dependent on how good your forecasting is, and if your forecasting is not good enough, or if some unexpected event happens, such as a storm, your network falls out of place, and you need to keep and with these things, you need to keep a good eye on what's happening and the actual conditions of the network on the day. Deep reinforcement learning actually proves a way to do that by helping you use current observation data, real-time data, to provide near real-time or even real-time reactions to what's happening. So we will speak more about what deep reinforcement learning is and how it looks like in the grand scheme of artificial intelligence, and as well how we have used it during the research to minimize background leakage and burst leakage and their effects on the network. Now, deep reinforcement learning exists within the scope of artificial intelligence. Artificial intelligence is a broad term used to explain making the machines do things that we would do intuitively, such as identifying patterns, classification, and even knowledge systems or recommendation systems. So we need to be able to do that using artificial intelligence, and the main section of that is machine learning that I was just speaking about right now. So you have supervised learning, where you teach the machine learning, the algorithm what is right and what is wrong, and you expect it to follow that in the future. Or unsupervised learning, where the algorithm identifies what is correct and what is wrong on its own. Reinforcement learning is somewhere in the middle between the two, where you give it a reward based on certain states, but you don't really tell the reinforcement learning algorithm how to get to that state, how to, for example, in terms of water distribution network, how to keep leakage to a minimum. You will reward it for having leakage to a minimum, but you don't really explain how to get there. So that's why we call it a semi-supervised learning algorithm. And it's reinforcement learning on its own proved in my early research with Q-learning to be too slow to implement into water distribution networks. It took weeks to use a Q table to find the best pressure settings for a couple of days. And what we want is to reduce the effect, to reduce the computational load and be able to use reinforcement learning properly. And that happened around 2015 with Google DeepMind, where they used what is called deep Q network. So this is using the Q learning algorithm by using deep neural networks to solve that issue. As a result, the function approximation power of deep neural networks has helped reduce the computational load by a lot. And as a result, deep reinforcement learning became something that's actually feasible. And when before it was something that is interesting, however, we cannot really use, through the use of deep learning and deep neural networks, this can finally be a reality. So since 2015, or even maybe a couple years, 2014 onwards, this has been the focus of Google DeepMind, the focus of Meta, and the higher technological companies that realize the potential of using deep reinforcement learning in our day-to-day applications, including and especially engineering applications. Now, deep reinforcement learning, as I said before, there's a new publication called Deep Reinforcement Learning Challenges and Opportunities for Urban Water Systems, where I have tried to the best of my ability and the available research to classify reinforcement learning methods. They include model-free and model-based methods. So if you've designed the model into the environment, you can actually follow it. That tends not to be the case and tends not to be the interest of research as model-based methods. Most of them are model-free, and in a sense, where model-free takes up most of the research and is the most common case when using reinforcement learning algorithms. So you have on-policy and off-policy value-based or gradient-based and gradient-free policy-based algorithms. So value-based algorithms depend on the value of your current state. Policy-based is where you're focusing on the overall policy that you want your reinforcement learning model to follow. There's a lot of algorithms there. Personally, we will be focusing on advantage actor critic today and proximal policy optimization to show how we use these base models. There are more interesting models and more complicated models that can fit the application that we have used later on in the research. But these are the base models just to give a little taste of how using deep reinforcement learning can actually change the way that we look at leakage management. So one of the examples of the advanced algorithms is distributional reinforcement learning, where the value is distributed based on the states. It gives you a better idea of how certain states affect the value and which states are actually much better than others. Where your word can be something very simple, your states and values should be quite complicated to account for the different ways your environment can look like. Now, understanding deep reinforcement learning is very important. However, it might seem very difficult when I'm using their terms, and obviously the delegates might not understand these terms or might not have heard of them before. So what I'm going to do is explain the formalism that we're using, and that's called Markov decision process. And once you understand the formalism properly, you find yourself 2 steps into the world of reinforcement learning already. You find yourself already understanding what the papers being published and understanding the general idea of deep reinforcement learning. And it's actually quite simple to wrap your mind around. What we have in front of us is 6 essential key terms to understanding deep reinforcement learning, starting with the agent. And as written in the presentation slides, you can see that the agent is a physical component that interacts with the environment. So in our idea of water distribution networks, and this is what I'm going to contextualize each term to, we are talking about some sort of actuator, since as mechanical engineers, we all understand things in terms of what we know. An agent has to be an actuator, has to be something that can take action and influence the environment. So if I'm talking about pressure management, then I'm talking about the valves. And if I'm talking about, for example, asset management, then I want to talk about pipe conditions. So, or I want to talk about a recommender system where this agent is not actually something that's there. I'm talking about how I'm talking about the user, myself, changing the pipes and placing new pipes or mending the pipes, and how this will affect the overall environment. So if you have a look, it's the physical component that interacts with the environment through actions, and as it enacts its actions on the environment, it receives observations, it receives feedback in a loop, and also receives the associated reward given to it by the designer or the programmer, which in this case would be myself or whoever is designing this algorithm. So that can appear as valves, pumps, or reservoirs. Now, when we talk about actions, what actions could you imagine happening in an environment? It must be stuff that we talk about on a daily basis, such as higher speeds for our variable speed pumps, or switching our fixed speed pumps on and off. Could be changing the settings on our pressure valves, or it could be stopping inflow or outflow to reservoirs. So actions can be continuous or discrete. So for example, switching on and off fixable speed bumps, that's a discrete action. However, variable speed bumps can have uh, speeds from 0 to 100%. So we can choose where in the middle. So in this case, your action space being continuous or discrete actually influences which algorithms you can use in deep reinforcement learning. So this is one of the more important decisions when choosing or when designing your deep reinforcement learning algorithm. You have the actions themselves, so open close valves, like we said, change pump speeds, or even shut down the pumps. If we have a look at the environment, which is the next step, uh, in the most general sense, the environment is our universe. So it's everything around us. How will it affect everything around us? But in in the sense of an engineering application, we're not going to see how changing a valve will influence my weather routine today, or whether I'll have breakfast or not. We're trying to focus on things that actually make sense and that actually apply to our application. So what we're looking at in our sense is either the water distribution network as a whole, so a whole system zone, or we're trying to look at district metered areas. So if we're talking about this DMA, then how will changing the valve in this DMA or the input valve or the output valve or somewhere affect our average zone pressure or affect our leakage management. So we're talking about the environment. Now, the environment can be the actual environment in a physical space, or it could be a model or a digital twin, which is the current trend of any industry right now, is to create the digital twin. So having a digital twin obviously helps because you don't have to apply these changes into the real environment until you're sure and you're confident, and helps with experimentation. So in this case, we used a model through the hydraulic software EPANET that actually models a current network in Lumley, England. So again, as I said, an example of the environment could be DMAs or zonal networks. And then we have the observation. So the observation is the feedback. So that's the pieces of information that are relevant to the agent. That's the data that we get back in a loop, telling the agent, well, when you changed the speed of this pump, you influenced the average zone pressure, you influenced the flow in these nodes, and you've caused such and such, or you've solved such and such. So this is we're not going to give the last conclusion, but what ends up coming back with observation is a set of numbers that explain the state of the environment to the agent. So what we're trying to achieve with this observation is some numbers that explain our state of the environment, or what the numbers that are important to us. And when we're looking at leakage management, one of the most important numbers that we're trying to look at is pressure. So whether it's average zone pressure or nodal pressures, we're trying to relay back pressure figures to the agents. So as a matter of fact, deep reinforcement learning is not one of the most data hungry algorithms, but it still requires some sort of nominal data that helps the agent understand the environment. And the more that you hear me speak about this, the more that you start realizing that it sounds like our day-to-day interactions. We look at how our actions affect our surroundings to decide whether the action was good or bad. Now, in this case, in water distribution networks, that could be, as I said, pipe flows, energy consumption, leakage values, even carbon emissions. If you wanted to, you're trying to keep it close to the case that we're trying to do. And in this case, it's leakage management. So pressures, flows, and the leakage values are the most important. But as we're all trying to reach a more carbon zero or carbon net zero um, water networks, or even practices across all of engineering, we are trying to make sure that our energy consumptions are low and maybe even explain in some figure carbon emissions. Our reward, so our reward is the purpose of the purpose of our agent. All he wants to do is collect rewards. It can be modeled as the candy that you give a child after they start walking, so they realize that walking is a good thing. So now this is positive reinforcement or negative reinforcement, and hence the name. So you can have negative rewards, penalties, to explain that this action that you just did or the agent just did was not good, it caused more leakage, or a positive action. Now, the rewards and reward formulation is one of the highest places of research right now in deep reinforcement learning, as there is no one way to decide what the reward should be. This is very specific to the application. And in our application, the reward was based on leakage rates and pressure violations mandated by OFWAT. So as you can tell, that won't be the same type of reward that you will get for autonomous driving, which is the focus of Waymo, which is an alphabet company run by Google. So rewards are quite different for different applications, and you should customize it to model the application that you're on. So the reward can be given for less pressure violations, lower energy consumption, less leakage, anything that's good, anything that you're trying to promote to your algorithm. And finally, have policy. So policy defines how the agent behaves. It's basically our desired output. So what we're trying to do is develop a deep neural network that understands how to behave given any state or any observation. It can tell you exactly how to behave within this environment and what to do next to get the positive reward that you're trying to do. So that is sort of the output of the algorithm. We're trying to get to the optimal policy, the best policy that the agent can behave with. Now, if you remember earlier, we said that there's policy driven or value driven. Value is equation of the reward. So policy driven is basically when you're focusing on the objective function of the policy and you're not using the value of the current action to dictate it. Whereas value driven is a step-by-step process. They're both equally as important, um, except in nowadays there's more work on either policy-driven algorithms or hybrid algorithms, where you use both policy and value to decide. And in this case, policy is the policy that we're trying to find is advanced pressure management. Some other policy, the one that was highlighted earlier in the table, was advanced pressure pump control. You can have the policy that you want to promote to the company. So if you're trying to get pressure management to be better, then that's what you're trying to reach with your policy. And that's the general understanding of our market decision processes, how to deal with it. Now, when we're talking about deep reinforcement learning applications in the water industry, this is 2 out of the 4 branches that is written in the review paper that I mentioned earlier. It's fairly new in the water industry, and other than the electric grid, which is not really part of mechanical engineering, they don't know many applications of deep reinforcement learning in research in engineering. They're mostly led by computer science research fields, such as working with deep reinforcement learning in autonomous driving is one of the bigger things. But the successes of deep reinforcement learning are quite vast. For the last, I think it has been now 9 years, even 10 years, where deep reinforcement learning was a trend. in artificial intelligence, and during that time, it has surpassed human level chess playing, Atari playing, so the games, and so in terms of actually cognitive functions, it's actually beat chess masters, and it's beat people in AlphaGo. So I don't know if you also if people know about some of these games, but everyone knows chess. Everyone knows its ability in stock predictions, so you can predict the future stock prices to a good degree using historical data, and that's what we're trying. And then, as a result, act on buying or selling the stocks that you're looking at. So you can train an agent to do these things for you. I think in the last year I've reviewed 2 papers that were doing that, and even to detect malicious speech on Twitter, which is now X. So there are lots of different applications for reinforcement learning in the wider industry, but in the engineering sense and in the urban water management, we have water distribution, stormwater, raw water treatment, and wastewater systems. These are the main focuses. This is just 2 of them. Today, we're looking on the right branch, water distribution, and we're going to give you an example of deep reinforcement learning and pressure management. So that's the 3rd bullet point. Now, how does this look like in water distribution network? So if you can have a look at the schematic in front of you, we have the environment in the center. That is the most important part in deep reinforcement learning. This is the part that dictates how the agent behaves, how the environment responds, and what reward you want to place for it. And as important as it is, it's the most central piece of our research and most central piece in designing any deep reinforcement learning algorithm. And the environment has to, in some way or the other, model the engineering application that you're talking about. And as engineers, we tend to have a lot of models that reflect that. So we're talking about fluid machinery today. You'll find modeling capabilities on ANSYS, and you find modeling capabilities in water distribution networks on EPANET or OpenGEMS or other what's it called, water gems, and other modeling software. There's one that's quite on the up called KTM. I think it's one of the best modeling softwares there. So the modeling software EPANET takes in raw data through SCADA or geographical information systems to build the model. The model is then uses our laws of physics and hydraulic laws to understand what the nodal pressures will be, where the leakage will be, and how effective changing pressures can be on the leakage. So obviously the environment has to communicate with the model to explain whether this new VAF setting was good or bad, and also relay that information back to the agent. And the agent itself is consistent of a deep neural network and optimization functions that help you decide or create the policy. So the new state is given to the agent. The agent then, through the state and observations, predicts what the next action should be. The action is then sent to the environment. The environment sends that to the modeler, or in itself, because the model is actually part of the environment, decides whether this is good or bad, and sends the information back as observations and rewards. So here we have, this is an example for the environment. In our case, our desired policy was advanced pressure management. We had two main things that we're trying to focus on is to minimize leakage, so leakage reduction. And if you remember, part of leakage prevention is actually pressure control. So it's to reduce the effects of leakage that we know that is in the system, and reduce pressure violations to keep all pressure nodes between 10 meters to 70 meters. We do not want it to go less than 10 meters, because that's a pressure violation with the regulatory bodies, and that will mean too high of a flow yes, it will decrease leakage, but it's not acceptable for water distribution networks, and it will also affect the asset life cycle. So we will reduce our life cycle of the assets, because as you can imagine, high flows in tight pipes could mean that the pipes will burst or create more leakage. So we're trying to keep it in this zone. And 70 meters is too high for pressure anyways. That could cause more leakage. So we're trying to keep it as low as possible between 10 meters and 70 meters. So our reward includes both of these numbers and figures into it considers both of them basically into the word, incorporates both. As you can see on the right, the issue with designing deep reinforcement learning algorithms is that you might not know what's happening until it's done. So we created a couple of render functions. You can see on the top right corner of the figures, reward distribution over the junctions. So in this case, we have, I think, 23 junctions. And you can see where it's received a lot of rewards and where, for example, in junction 13 and 14, where it hasn't received as many rewards. You can see how the settings changed in part C, in the bottom left corner. You see how the settings of the valves have changed. So at the beginning, we start at 40, and then you can see that sometimes it decides that V31, valve 31 should be going up and down. It should be going higher in minimum night flow and it should be going lower during the day. V1 should be low during minimum night flow and high during the day. So different valves, depending on their locations, have to behave differently. And on the right, you see figures for the average pressure before and after action. So red is before, blue is after. Average water loss, so leakage before and after. So you can see that we've decreased leakage exponentially, we decreased leakage a lot through our actions, and the average flow. So the agents that we're looking at, today's agent is not asynchronous actor critic, it's actually called advantage actor critic. That's a typo. And it's an on-policy model-free DRL algorithm. So on-policy means that it improves the current policy rather than rather than changing the policy. So it keeps improving the current policy, and it's a hybrid method. So what it does is it has an actor neural network and a critic neural network, so two neural networks. Whilst the actor neural network follows the policy-driven methods that we talked about earlier, so it just focuses on reducing policy gradients and finding the best objective function for the policy. The critic neural network follows a value-driven method. So it criticizes the action that the actor has done. So they go in a loop that is connected through a temporal difference error, where the actor acts and the critic decides whether that was good or bad. And then as a result, tells the actor you should do this better or that better. And in this communication loop, it makes things a bit better. Makes the performance a bit better. So we have two results: a result in minimizing background leakage and a result in minimizing burst leakage. So in this case, we're talking about burst leakage. So we have three randomized nodes that are fully disconnected because of either a storm or because of a burst that hasn't been detected yet. They released leakage, and what we're trying to do is reduce the leakage in that. And as you can see, the deep reinforcement learning algorithm, the advantage active critic, before hyperparameter tuning and after hyperparameter tuning differs. So on the right-hand side, these are the performances. These are the step rewards. You can see in blue, dark blue, you can see it before, and red blue is after. They compared to benchmark optimization algorithms. So you can see that it performs quite close to differential evolution and particle swarm optimization, which are the current practices. On the other hand, on the left-hand side, you can see the processing times, and this is the main contribution of deep reinforcement learning. The processing times are reduced significantly, making it close to real time for implementation. So what happens with deep reinforcement learning is that you have to train them for a while. So these are the ones in light blue, green, and dark red. So these are the training times. So that's what you do behind the scenes, but actually implementing them and the test times, these are the very small bar graphs on the top of the graph. So this is how long it actually takes to run these models on your water distribution network or on your digital twin. As a result, A2C has reduced burst by 32.48%. So it reduced the effects of leakage by 32.48%. So therefore, more water saved, more energy saved, and more carbon emissions saved. And then the tuned advantage actor critic actually produced the second best result. So under differential evolution. Now, what does that mean in terms of time? We have managed to simulate to 72 hours in 24.88 seconds. So 72 hours of simulation, each hour dealt with separately, has been solved in 24.88 seconds, meaning that it can give you an answer to what you should do now in less than 0.4 seconds, making it a real-time model in this scenario. Now, whether it's going to behave in real time or near real time depends on the complexity of the model that you're dealing with. This was a medium-sized DMA, 22 nodes and a couple of pipes, so connecting all of them, and 3 reservoirs. So as a result, this was simpler, but on a real network, this can go up to, I think in my experience, it went up to 4 seconds. So again, it's a scalable optimization algorithm, but how close it is to real time depends on the complexity of the model. And on the second part, you can see the background leakage. So you can see whether these are leakage events that cannot be detected by our current practices. So we cannot really find out whether there's a leakage there or not. Now again, it performed quite highly, the advantage active critic, and we reached an average of 67.17%. So got the highest reduction in background leakage. Now, background leakage before this was not addressed properly in water networks, and now you can have a method to mitigate for background leakage without finding where they are, because the leakages themselves, even though they're quite small, they go on for a long time and they can exist in a lot of pipes, but you won't be able to fix them. Now, again, these ones perform real time because the model itself was simple enough to deal with that. However, again, it can, depending on the complexity of the model, is how well it performs. Nevertheless, in terms of computational cost, deep reinforcement learning are much better than the actual current practices. And the other algorithms used in these two experiments are proximal policy optimization, which is purely a policy-driven algorithm, and recurrent proximal policy, where we use a long short-term memory module, so LSTM module, on the proximal policy optimization to realize long and short-term dependencies. So as the word suggests, so you realize dependencies of how you act today, how you act right now with future rewards. So it kind of is a feedback loop within the neural network. Now, how does deep reinforcement learning, so this is a concluding slides, how does it affect, how can it affect our practices? Deep reinforcement learning compared to our current practices is more data efficient, performs really highly, and can actually get us closer to real time, which is what we're going to try to reach once our digital twins are established. And it can also be adaptable. You can retrain them to accommodate for different models and accommodate for different networks across. So there's a chance to use transfer learning to teach new networks and new applications using older applications. So we can use this network that I've created, can use what the neural network has reached to teach neural networks. newer neural networks. And what could that lead to in the water sector? Again, so many things could lead to from proper management of our pressure in the water sector, such as water preservation, accounting for the new customer demands, because now that everyone is going more towards the urban areas, we are going to be we're going to be left with extra load on our network, so we can actually start accounting for that now. And promoting net zero carbon emissions is one of the industry favorites, and it's one of the things that we're all trying to reach. So for the future work, we can test different algorithms on different networks of sizes and topologies. You can reach out to me so that I can tell you how it went with bigger networks that contain about 2,000 nodes, serving a larger area with more pumps and valves. And I can tell you right now that it worked really well. Using multiple agents, that's a current field in deep reinforcement learning, and also experimenting with different objectives and different policies. So thank you guys for listening. I'll be around hopefully to listen to all of your questions.
Okay, thank you very much indeed, Ahmed, for this excellent presentation. And also keeping the time constraints within the time constraints of this webinar with this excellent timing. So we have heard from Ahmed on this webinar that deep reinforcement learning has the potential to tackle complexities that used to be very challenging, as it relies on deep neural networks for function approximation and representation. So this technology has many fields due to its impressive results and can effectively revolutionize the water industry. This webinar focused on the findings of Ahmed's 3-year doctoral research and involved various applications of deep reinforced learning in the water industry. And also it highlighted how using DRL algorithms minimize leakage in pressure management case studies. And definitely this ability for unsupervised learning makes deep reinforcement learning a great tool for the instantaneous optimization. So now we have time for questions and answers. Please type them on the chat box, and let's start with the first entry here on the chat box from Craig Walker, from Principal Asset Manager from Enova. The first one is a comment, not a question. Another very important outcome from effective asset management is that this kind of insight enables you to understand how to change future designs to prevent and minimize the failure mode in the first place. And the use of artificial intelligence will give much greater asset intelligence. Ahmed?
Yeah, I fully agree with that. There's a lot of work to preventing, and this is where our proactive team should be working on, is to prevent future leaks from happening. Basically, the healthier our asset health is, the less that we have to be concerned with leakage. So there's a lot of AI work on that, and it's mostly dealing with classification. And there's also a chance for deep reinforcement learning to be used in that through recommender systems to recommend whether you should do this or not. This doesn't need the computational efficiency that is given by deep reinforcement learning, but will work well with the knowledge that it can build, the intelligence that it can build. So whilst the research that I've been talking about has more focused on real-time behavior and trying to get it closer to real-time, asset management can work real-time, but it's not as important, or it's not as much of a priority.
Lovely. Thank you very much, Ahmed. Then Craig Water states, traditionally, data capture was limited from assets due to cost and technology limitations. How do we ensure that when creating new assets, we include means to capture the data that can help feed these models efficiently and effectively both now and into the future?
So I've in some of the summits that I've attended, including the Global Leakage Summit, there's been a lot of work and a lot of research from companies even abroad, such as Muller Systems and even some at home, that work on producing more sensors that can actually be cheap, affordable, and can have a longer battery life that can be placed in the water distribution networks as they are right now. One of which that just sprung into mind was a fiber optic system that are inbuilt to the pipes that the water distribution networks sell, that can almost measure anything that's happening from the start to the end of the pipe, including the flow, including any maybe what's it called, any damage that's being done by traffic, by the storm conditions, by soil movement. So it gives a very, very detailed look onto the assets that are in the water networks, and almost renders even algorithms less useful because you can see immediately what's happening. Putting that with the artificial intelligence algorithms will give you an almost instantaneous look into what's happening into your network every day, which is honestly what we're trying to get, because some of these networks are 400 years old and we don't even know where most of like most of the valves are.
Lovely. Thank you very much, Ahmed. Next one is just a question from Sweta Yadar, PA Consulting. Are you going to share this presentation?
Yeah, of course. I think we
Okay.
have. I think I have one on my ResearchGate that's quite similar to this on my ResearchGate profile.
Okay, and then we can discuss
You can
after the
also share
event
it.
if you stay behind with the IMechE that you can contact either directly Ahmed or
Of course.
the IMechE to get it. Then the next one is Charlie Patterson. How do you balance the priority for the training between reducing leaks but also delivering water to the customers? Turning off all the pumps would reduce leaks to zero, but is clearly not very helpful.
So I think towards the end of the slides, I might have rushed over that part, but I've explained two objectives that I've used personally in my rewards to specify that obviously reducing the like increasing pressure to a maximum and therefore reducing flow can be bad to the network, and reducing the pressure to a minimum and just put some pressure violations to ensure that the water still flows in the network in the way that we as engineers deem well. So in this case, in any case that we're going to use deep reinforcement learning in, this has to be included in the rewards, where a highly negative reward or a penalty is given to undesirable states or undesirable actions, such as turning off all the pumps or reducing the leaks to zero. It could also be coded into the agent's behavior that they cannot even do that. It's not part of the action space. So it's either to remove it entirely from the action space, there is no action to close all the pumps, or to include it in the reward and keep it as an option. So if it's something that is considered high severity or high risk, you can remove it entirely from the action space, or if it's considered undesirable, you can make it undesirable in the reward. So again, this is part of reward formulation, which is after the environment design, is one of the most important research areas and one of the things that should be spent most time on. So I hope that answers your question.
Yeah, thank you very much, Ahmed. The next one from Charlie Patterson. Is there a danger when using this approach that the changes made to the agents are too extreme, trying to explore the parameter space too fast and lead to unintended system issues?
So the dangers when it comes to deep reinforcement learning application is the same as any machine learning applications. And through the work of machine learning operations, MLOps, what tends to happen is that we build these algorithms in the back end. Like at home, we don't really deploy them until they're deemed 100% safe. So exploring the parameter space, for example, is something that it does on the models and not on the real network. So it will explore, learn everything that it has to learn. And then once the model is fully built, that's when it's tested to see whether it's actually feasible to use. If it's not feasible to use, it's scrapped and you need to start over again, or you need to find out what's happening that's wrong. So it cannot be sent out for deployment, which is the final step after testing, after validation, is to deploy it into the engineering system. So that is done after all these checks are made. And since safety and safe practices are they're the most essential part of any engineering system, we cannot afford to introduce these dangers into our network. So they were all done through models, digital twins, and through experimentation before they're deployed. And that will be the work of the data science team. So to focus on making sure that these things are not deployed into the system if they're not ready. That's all.
Lovely. Thank you very much, Ahmed. And this is the last question I have on the inbox here, which is very timely because it's exactly 1 o'clock that we planned to conclude this webinar. I would like to thank Ahmed, the IMechE, for facilitating this webinar, Ahmed for presenting, and yourselves for attending this webinar. If there are any further questions past this webinar closure, please pass them over to the IMechE, and then they could email us at Lancaster University for a response. Thank you very much, everybody, for attending. Goodbye.